So today we're going to look at section 2B, problem solving with units. As we've talked about before, units can be really helpful in terms of solving a problem correctly. First thing I always recommend that you do is identify the units in the problem and the units that you expect your final answer to be in, and then use those units to help you determine a strategy for solving the problem. And ultimately, as you're working through the problem, make sure that as you're doing your unit conversions that the units that you wanted to get rid of actually did cancel out appropriately. So I'm going to look at a couple of examples here. We'll start with example 1. It says you're buying 50 acres of farmland at $10,000 per acre. What will the total cost of this land be? So in part A, it says, well, what units do you expect your final answer to be in and why? And, for example, here you can see the question is asking what will the total cost. So hopefully you would say, well, I expect my final answer to be in money because the problem is asking for total cost. If I want the solution to this problem, then I start with what I have. I have this 50 acres. Again, like we talked about yesterday, if you don't have a fraction, put it over 1, make it a fraction. You know that you want to get rid of those acres and end up with money, so if I want to get rid of those acres, I put acres on the bottom and put money up top, and we can see from our problem that we have a direct conversion here because it costs $10,000 for every 1 acre. So for every 1 acre, it will cost us $10,000. That way now, at this point, acres have canceled out. I multiply straight across. 50 times 10,000, that's going to give me 500,000. And the only unit I had left was money, so that therefore my final answer is dollars, $500,000 for the 50 acres. All right, examples 2, 3, and 4 are much the same. I'll let you reference the solution key for those. We'll scoot on down, though, to number 5. It's a little different. You'll want to reference on your formula sheet the energy conversion. So you can see a calorie to joule, a watt to a joule per second, and then a kilowatt hour is 3.6 million joules. So we'll be using that part of our conversion sheet at the moment. So, looking here at example 5, riding a bike burns 50 calories per mile. If you ride at a speed of 15 miles per hour and you travel for 1 hour, we want to know what is your average output of power in watts. So, since we want our answer in watts, we'll go back and look at our formula sheet here. In our formula sheet, you can see that to get to a watt, I'm ultimately going to need my answer to be in a joule per second. So the only way to get to a joule per second is looking back at joules, and joules start at calories, and you'll notice that that's what our answer is right now, or our problem is starting at calories. So let's start with that 50 calories per mile. And I can figure out how many calories per hour by using the conversion sheet that has been, or the conversion that's been given to me in the problem, that I know that I travel 15 miles every hour. So I can get rid of my miles by putting miles up top and hours on the bottom, and I can travel in 15 miles for every 1 hour. Then at that point, my miles have canceled out, and if I multiply straight across, then I know that I'm burning calories at a rate of 750 per every 1 hour. Now I've got calories per unit of time. So if I could get myself from calories to joules, and looking at your formula sheet, you certainly can go from a calorie to a joule. That's going to get me closer to getting a joule per second, which will get me back to my watts, which is what I want. So calories per hour here. I want to get rid of those calories since calories are up top. Put it diagonally on the bottom to cancel out. We can go directly from a calorie to a joule. It says on the formula sheet there are 4,184 joules in 1 calorie. I'm going to keep on with the chain here. At this point, calories have canceled out, and I have joules per hour. Like you saw on the formula sheet, you need to get to joules per second. So let's get rid of those hours. Hours are on the bottom. Let's get rid of them. So we put it up top. We can go from hours to minutes. We know that there are 60 minutes in 1 hour. Then at that point, the hours have canceled out. And we just keep going because we need to get to our seconds. So one more conversion there. Minutes will need to be put on top to cancel out, and we can go to seconds, and we know that there are 60 seconds in 1 minute. Then at that point, minutes have canceled out. And then if we multiply now straight across, we have 3,138,000 over 3,600. After you do that division, you get 871.667. Since we're rounding to the nearest whole number, then we're talking about 872. Looking at the units that are left in the problem, joules up top per second. So this would be a joule per second. And then you may be sitting there saying, well, my answer is supposed to be in watts. If you remember back on your formula sheet, a joule per second is a 1-to-1 conversion. However many joules per second you have is exactly how many watts you have. So here for our problem, 872 joules per second is the same as 872 watts. Final answer. Okay, and we'll move on to our next page. At the top of the next page, you see a couple of different items. The first one is density. It refers to the compactness or crowdedness of a space. We'll refer mostly to population density in this class. And essentially, it's the number of people per unit area. It might be per square miles, per square feet, per square kilometers, but it's the number of people per square unit. Okay. And then concentration, we're looking at dosages of medicine. So they're recommended on concentrations per kilogram of body weight. So bumping on down to example 6, it says that Manhattan has a population of 1.6 million people living in an area of about 57 kilometers squared. We want to find the population density. Again, it's just the number of people per, means to divide, square unit of area here would be square kilometers. So if I fill in what I know here, I have 1.6 million people. So what that means is I have 1,600,000 people. And then I divide that by the 57 kilometers squared. And what I would do here is I would just go ahead and do that division. We're rounding it to the nearest whole number. So you should end up with 28,070 people per square kilometer. Okay. Now, example 7 and 8 do step it up a notch. All right, these will be where we'll be looking at our dosages for medicine. So those of you that are interested in the nursing, you may find some of this to be somewhat familiar or intriguing. In example 7, you have a child weighing 15 kilograms, and they have a bacterial ear infection. The doctor orders medicine at a dosage of 30 milligrams per kilogram of body weight per day. And so that is written in such a form like you see here in parentheses. 30 milligrams per kilogram day are 2 units, but they're both going to be on the bottom. This is the one exception to the rule of where you would have more than 1 unit on either the top or the bottom. And then that dosage is divided into every 12 hours. So in part A, we want to know how much medicine should the child be prescribed every 12 hours. So let's first figure out, well, how much are they going to get every day? So this child is starting out, they weigh 15 kilograms. And we want to know, well, how much are they going to get per day? You have your conversion factor here that they will get 30 milligrams of the medicine for every 1 kilogram per day. And if you notice, at that point, the units that are canceling out, kilograms, and that's the only units that are canceling out. And so then you can see, okay, after I multiply straight across, then I am receiving, or the child is receiving a dosage of 450 milligrams per day. And then the only thing that I need to do from there is, since I want to know, well, how much will they get every 12 hours, we know in a day there'd be 2 12-hour periods, so just divide that by 2. And we'll be looking at 225 milligrams every 12 hours. Okay. In part B, it says, well, if this medicine is to be taken by an IV drip with a concentration of 25 milligrams per milliliter, we want to know, well, how many milliliters should the child take every 12 hours? Well, you know how many milligrams they should get every 12 hours from our previous answer, 225 milligrams every 12 hours. I put the 12 hours in parentheses just so that you don't think whenever you do your multiplying straight across, you don't include that 12 as part of your multiplying. So 225 milligrams for every one 12-hour time period. And then we want to get rid of those milligrams, so we put our milligrams on the bottom and get to milliliters. And then we can see here that there are 25 milligrams in every 1 milliliter. And then, like you've seen before, milligrams are canceling out. The answer then we multiply straight across. We have 225 divided by on the bottom, 1 times 25. Go ahead and do that division and you should get 9. The units that you have left, milliliters, so 9 milliliters every 12 hours. Okay? And then we'll go ahead and look at example 8 down below. It says that a doctor orders 2,300 milligrams of Rocephin to be taken by a child that weighs 15 pounds 6 ounces every 8 hours. The recommended dosage, though, is 75 to 100 milligrams per kilogram per day. And we want to know, well, is the amount that's ordered by the doctor for this child within the recommended range? So here in part A, it says calculate the baby's weight in the correct units. You can see here that they've given us the baby's weight in pounds and ounces. However, the dosages are measured in kilograms. So whenever it's asking here for the correct units, then I need to convert these pounds and ounces into kilograms. There's a lot of different ways to do this. I'll show you one way, but just know that you could do this multiple ways. I'm going to start then with converting those 6 ounces into pounds. So start with those 6 ounces over 1. And to go from ounces to pounds, we can do that directly. And from your formula sheet, it will tell you that there are 16 ounces in 1 pound. At that point then, the ounces cancel out. You multiply straight across and you have 6 divided by 16, which equals 0.375. Plus the 15 pounds that we already have. So then we know, well, this kid weighs 15.375 pounds. Now I need to convert those pounds into kilograms. So put that over 1. We can go directly from pounds to kilograms, looking at your formula sheet. And your formula sheet would tell you that there are 2.205 pounds in every 1 kilogram. Multiply straight across, then divide. You should end up with 6.97 kilograms. Final answer is the weight. Okay. So then in part B, it says, well, calculate the amount of Rocephin prescribed by the doctor per day. So the doctor has prescribed 2,300 milligrams every 8 hours. So we just ask ourselves, well, how many 8 hours are there in a day? And there'd be 3 of those, so we multiply by 3. So I could say, here's the way I could do it. I could say, well, there are 3 8-hour time periods in 1 day. That way then those 8 hours are canceling out on you, and you do your 2,300 times 3, and the doctor has prescribed 6,900 milligrams per day. So then in part C, we calculate the lower end of the recommended dosage for this child. Recommended dosage is 75 milligrams per kilogram per day for the child. So since this child weighs 6.97 kilograms, we put that over 1. We can use our conversion factor there, that there are 75 milligrams for every 1 kilogram per day. And then you can see, like we saw before, our kilograms cancel out. We multiply straight across, and the lower end, then, this child should be recommended to be getting 522.75 milligrams per day on the low end. Part D, we just want us to figure out the upper end for this dosage for this child. So you start off with the child's weight over 1, and then you can see that the upper end is 100 milligrams for every 1 kilogram per day. We multiply straight across here, and you have 697 milligrams per day. You can now see that a safe dosage for this child is between these two amounts, yet the doctor has way overprescribed at 6,900 milligrams per day.